Here we will discuss the third step in the GIS project workflow, analysis. During the planning stage of the project, you'll want to consider the analysis needed and list the major steps in the process. That way, you can make sure you are aware of all the data sets you will need and can include them as you create the project database. You may also create a simple diagram of the process as a guide. A GIS is designed to support a range of different kinds of analysis of geographic data. We can examine and explore data from a geographic perspective, develop and test models, and present data in ways that lead to greater insight and understanding. With spatial analysis, we can visualize tabular data in a compelling way. Analysis ranges from simple to technical depending on the methods used or needed to gain answers. In this way, the term spatial analysis has a broad meaning, but simply comes down to taking a closer look at how two or more features on the Earth interact with one another. Thinking back to our healthcare facilities project and mental diagram, again, the questions we are trying to answer drive our analysis methods and tools needed to get the work done. Before we begin analysis, we need to know what we are looking for. We'll revisit our project later in the video. First, let's see what we can do with vector data. Remember that vector view of the Earth and its features are viewed and displayed in GIS as points, lines, and polygons. Pretty cut and dry features. Behind the graphics on the screen is an attribute table linking all of those features with descriptive details. The ability to select specific points, lines, and polygons on the map or screen and have those same features selected on the table makes GIS a powerful analysis tool. Let's say I'm addicted to Starbucks coffee and need to plan my vacation so that I'm always near my coveted cup of joe. I don't care where I go in the world as long as it's near a coastline. So I'm looking to locate all Starbucks in the world within 1 mile of a coastline. With access to a Starbucks store dataset and the World Boundaries dataset, I could join these attribute tables and create a simple query that would examine this now much bigger attribute table and pick out Starbucks within 1 mile of coastlines. The Starbucks locations found true to the query show up highlighted on my map and within the attribute table. Voila! I now have my vacation spots narrowed down. To take it a step further, I could analyze the data I have further or add to it by layering an annual average temperature dataset on top of that latest selection. Now I can ask which Starbucks are within 1 mile of the coastline and have an annual average temperature of a range of values, say 78 degrees. We'll take a closer look at each of these analysis tools in the following slides. Measurements are as straightforward as they sound. We can measure vector data in terms of distance, perimeter, and area. We can accomplish these measurements in GIS by using the measurement tool and through calculating area, which really calculates the geometry of each line segment first to derive the answer. This comes from the attribute table. Layer statistics. So how many Starbucks stores are there in the world? Layer statistics help us answer this question. The example here is not for Starbucks locations, but I've included it here to show you an example of what a basic stats results looks like in GIS. From any selection we make in GIS, we can view stats like these, showing minimum, maximum, sum, and distribution. GIS isn't all about maps. Sometimes a simple graph or calculation result is all we need. Geostatistics simply means statistics involving the space, geographic space component. Traditional statistics doesn't consider where the data is on Earth or deal with distance from any one variable to another. Statistics tool in a GIS allows us to run statistical analysis that does consider space. We won't go into that here, but just know that it can be done. I've already given you an example of what a query in GIS can accomplish when describing my coastal vacation scenario. Here is what the tools in GIS, specifically ArcGIS, look like. The Select by Location tool is shown here, and as you can see, there are many options to choose from. This selection reads the chosen attribute table and picks out the data meeting the query we built. If you look at the map, you can see where a bright greenish line is highlighted, which represents the resulting selection. Queries help us answer the basic questions of what is nearby this thing or where do these features overlap. With each selection we make, we narrow our results and come closer to an answer. Each selection we make can be made into a new layer of its own, so we are looking at and analyzing the data we are interested in. Creating a buffer in GIS can be the starting point for many projects to simply identify a study area. Looking at the image, we consider a fictional analysis of zombie outbreaks in Monmouth County, New Jersey. This buffer analysis Dr. Gonzalez-Tennant is conducting considers the average pace of a zombie at 1.5 miles per hour and the tendency for today's zombies to occur from the result of some kind of pandemic. So that squares on the map represent hospitals and emergency facilities. As you can see, buffer analysis places radiating circles corresponding to expanding distances or times around the various medical facilities. Each ring on the buffer represents 1 hour of zombie travel time at 1.5 miles per hour. First ring is 1.5 miles, second ring is 3 miles, and the outermost ring is 4.5 miles. Okay, so that's useful. But from here, we can adjust the transparency of the buffer layer and quickly see which cities and populations need to stock up on ammo or evacuate. But we can make this better. If we dissolve the buffers, we can better see where the hordes overlap and see a clearer view of the entire selection. If we create a new layer from this dissolved buffer, we can calculate area of the whole much easier. Now, if you're thinking like a GI scientist and have watched your share of zombie movies, you probably realize that this buffer analysis is missing something important regarding mode of travel. Present-day zombie hordes are more likely to roam along streets than along open fields, bodies of water, or similar. We'll come back to this in a minute. I think of topological overlay, or the layering of features on the Earth, like a delicious sandwich, for multiple sandwiches depending on how hungry I am. Now, there are several tools available in GIS software that will allow you to modify and analyze your layers to view multiple features and to see how they are related to one another on the Earth. Vector overlay is a practice in geometric imagination. Pretend your sandwich is made up of different map layers of various sizes and shapes. We have soils, land use, city boundary, homes, ice cream shops, roads, sidewalks, and so on. The clip tool, indicated as letter G on the image, acts like a cookie cutter. Imagine using a cookie cutter on your sandwich of many layers. The result would include only the parts of the sandwich fitting in the shape of the cookie cutter. A cookie cutter in GIS can be any polygon type layer. The boundary of your study area, say city boundary, or a boundary you created from a buffer, is a good example of a layer you could use as a clip. Something important to know about applying an overlay to your data is that the resulting selection doesn't combine the attribute tables of those layers. Each layer you've clipped, for example, will still be independent, just a subset of the original. We can use vector overlay analysis to single out data we need to display for further analysis. We'll practice using some of the more common operations in the lab assignment. If you're thinking there is no way you'll ever remember all of these options, it's okay. We all need help. There's definitely operations available that are rarely used. Knowing the common operations will take you pretty far. Now for a bit of GIS magic. Sometimes we need to transform or reclassify vector data in order to conduct more meaningful analysis. I'm not going to go into great detail about this, but at this point you just need to know that it's possible. A transformation of vector data happens when you want to view multiple points as a line, or we want to apply a buffer to a single point and use it as a polygon. We can also transform vector data by converting polygons to rasters. We'll learn more about raster later in the video, but the example shows what the result of a raster polygon looks like. Distinct lines become generalized pixels. Reclassification is typically used to simplify a data set so we can view and analyze it easier. It's as simple as saying now all the colorful clothes in your closet will be called happy clothes, and all of the black, white, gray, and otherwise dull colored clothes will be called indifferent. We put data into new categories to suit our purpose. For a more applicable example, we can take a land use data set, which typically includes more than 20 different classes, and reclassify it to only 2 classes. For example, forest would get a value of 1 in the attribute table, and no forest gets the value of 0. That way you can isolate forest. Now we can easily view and calculate the area of forest or non-forested areas within our study area. Network analysis is applicable to several business and utilities scenarios. A network can be a road, power line, sewer line, cable line, river, or essentially any connected line segment. You've likely used a form of network analysis and haven't realized it. Your smartphone displays the result of network analysis when it tells you how long your commute to work will take you right now. The electricity running to your home or work is monitored by network analysis. FedEx and our delivery services save a ton of money by using network analysis to plan routes. Businesses use network analysis to match the supply of demand for their product through a road network. It can also be used to trace the flow of goods or information through a network of lines. Each line in a network is called a line segment, where the line segments are connected by nodes. Imagine a node as a turn or intersection where 2 or more roads meet. We can make certain line segments more important than others and set restrictions, like one-way streets, on-line segments to create a desired path. We could also add a cost component per mile or line segment to further define travel time along a route or path from point A to point B. Let's revisit the zombie outbreak scenario. We can use network analysis to create an area or polygon which encompasses all accessible streets within a given distance or time. This is also referred to as a service area analysis. It takes into account the placement of streets and is useful for deciding where to place a new business or warehouse. So the zombie horde, they're more likely to travel streets than open land or water. Network analysis can take into account features of the landscape like slope of the road and calculate distance. The result we end up with looks like the map here, where the buffer follows the road network versus covering a circular area. It gives us a clearer picture of where zombies will most likely be wandering. If you're interested in this application of GIS, be sure to check out Dr. Gonzalez-Tennant's site, where I retrieved the map images and example from. This project is shared with me by one of his extended family members, a former UWF student. It's a fun way to describe what GIS can do. Before we move on, let's bring it back to the GIS process and how vector analysis might be applied to our healthcare facility project example. Considering the questions we need to answer and the data identified, we could conduct the following vector analysis to gain answers. We could query to find all the hospitals within ER. We could buffer to identify a radius of 10 miles surrounding each healthcare facility. We could transform the census tracts layer into a population distribution raster. We could clip the population information within the buffer to determine the number of people within a 10-mile radius of each facility. We could also perform an origin-destination cost matrix, finding the shortest distance or time from the center of the census tracts to a healthcare facility. The results shown here might be what our results would look like. Can you identify key terms and guess how some of the features were created just by looking at the map? Next up is raster analysis. It's a completely different view of the world. In grid-based analysis, the spatial coincidence and juxtaposition of values among and within maps create new analytical operation, such as coincidence, proximity, visual exposure, and optimal routes. These operators are accessed through general-purpose map analysis software available in most GIS systems. While the specific command syntax and mechanics differs among software packages, the basic analytical capabilities and spatial reasoning skills used in GIS modeling and analysis form a common foundation. Raster analysis can treat cells locally, by neighborhood, or by zone. Distance measurements use one raster layer results as another raster layer where the attribute of each cell is a measure of distance. The higher resolution raster creates a more accurate measurement. Local raster operations are performed on a single data set on a cell-by-cell basis within a defined range. It computes output cell values as a function of the input cell values. It can be done using single or multiple rasters and computes simple math algebra like addition, subtraction, finding the mean or max values. Typically, this is called reclassification. In this example, we reclassify the elevation raster for slope that are suitable for sledding. We assign a value of 1 or 0, effectively true or false, where 1 means the slope meets our criteria, and 0 means it doesn't. When you convert the parks vector layer to raster and reclassify it for accessible versus non-accessible parks, these two layers will help us narrow down our search for accessible parks that are ready for sledding. Raster map overlay is when local operations are applied to multiple raster layers, also known as map algebra. Back to the sledding example, say we multiply the slope layer by the parks layer, equaling a new grid. For the slope, 1 was optimal slope for sledding. For accessibility, 1 was accessible. So 1 times 1 equals 1. And 1 in the new layer would mean that these areas were both accessible and the slopes are good for sledding. 0 would mean that one or both of the parameters were not met. No data areas are not included in this analysis. Most commonly, this is used for suitability modeling or weighted analysis. When visiting every location in a study area isn't possible or is too expensive, using spatial interpolation to predict those values in between known points. Examples here are rainfall, elevation, and concentrations. Neighborhood operations are performed using a moving group of cells surrounding a focal cell. There are four types of neighborhood operations: quantitative, calculating minimum, maximum, mean, and standard deviation; qualitative, filtering, and edge enhancements. The filter tool can be used to either eliminate spurious data or enhance features otherwise not visibly apparent in the data. Filters essentially create output values by moving overlapping 3 by 3 cell neighborhood window that scans through the input raster. As the filter passes over each input cell, the value of that cell and its 8 immediate neighbors are used to calculate the output value. A low-pass filter smooths the data by reducing local variation and removing noise. It calculates the average mean value for each 3 by 3 neighborhood. It is essentially equivalent to the focal statistics tool with the mean statistic option. The effect is that the high and low values within each neighborhood will be averaged out, reducing the extreme values in the data. The high-pass filter accentuates the comparative difference between a cell's value and its neighbors. It has the effect of highlighting boundaries between features, for example, where a water body meets the forest, thus sharpening edges between objects. It is generally referred to as an edge enhancement filter. The zonal tools allow you to perform analysis where the output is the result of computations performed on all cells that belong to each input zone. A zone can be defined as being one single area of a particular value, but it can also be composed of multiple disconnected elements or regions, all having the same value. Zones can be defined by raster or feature datasets. Some zonal tools quantify certain properties of the geometry or shape of the zone input and do not require any other inputs. Other zonal tools use the zone input to define the locations for which other parameters will be calculated, such as statistics, areas, or value frequencies. There is also a zonal tool that is used to fill specified zones with the minimum value found along the zone boundary. What can you do with a raster analysis? You can answer more complex questions. Find suitable locations for a new healthcare facility based on desired criteria. You can manage risks to the current facilities. You can visualize patterns of how the community accesses the current healthcare facility locations to increase efficiency, and you can model or predict costs in order to optimize growth.